Hello there, fellow math enthusiasts. Mrs. Delzati here. Today we're going to be working to use synthetic division to factor higher order polynomials. We're going to make use of some of the skills that we learned yesterday in order to do so. So first of all, a quick warm-up. I want to use synthetic division to divide the polynomial by the binomial. Since this is an x plus 5, the k value that I'm going to be dealing with is a negative 5. And then the coefficients that I'm going to be writing down are 1, 7, 0 as a placeholder, and negative 49. I'll drop down the 1. 1 times negative 5 is negative 5. I'll add down to get 2. 2 times negative 5 is negative 10. I'll add down to get negative 10. And then negative 10 times negative 5 is a positive 50. I'll add down to get 1. So I've got x squared plus 2x minus 10, and then plus 1 over x plus 5. Now I want to know, is x plus 5 a factor of this polynomial? And hopefully you're able to go ahead and say that no, it is not. The whole reason that we know it's not is because there is a remainder. Now yesterday we dealt with the factor and the remainder theorem. That look a little better there. We dealt with the factor and the remainder theorem. And with the factor theorem, we saw that x minus b will be a factor of p of x if and only if p of b is equal to 0. If the remainder equals 0, then the binomial is going to be a factor of that polynomial. All right. Now, this is useful when we cannot go ahead and we cannot easily group when we're trying to go ahead and try to factor a polynomial. So when we can't factor a polynomial by grouping, we have something called the rational root theorem. The rational root theorem goes ahead and gives us a place to start with our synthetic division. It gives us a list of possible roots that we could go ahead and we could check to see if they would be a possible root for the polynomial. Now the way this works is we go ahead, we take the factors of the constant, and then we divide them by the factors of the leading coefficient. The factors of the constants we go ahead and say are our p-values. The factors of the leading coefficient are our q-values, and we have plus or minus for both of them. Now the easiest way to see how this works is to actually go ahead and to do a problem. That's what we're going to do here. I want to be able to factor completely, and I want to find all the zeros. I cannot go ahead and I cannot group this 2 by 2 or 3 by 1 or 1 by 3. And notice that I didn't give you the first 0 this time, did I? So since I didn't give you the first 0, what we have to do is we have to figure out what some possibilities are. So we're going to go ahead, we're going to talk about our p-values first. The p-values are our factors of the constant. The constant is negative 3. And if we think about numbers that multiply to negative 3, well, we could say positive 1 and negative 3. We could say negative 1 and positive 3, which is why we would have plus or minus 1 and plus or minus 3. Do you see how this plus or minus is coming into play here? Now we want to find our q values. Well, our q values are the factors of the leading coefficient. The leading coefficient is 2. So I could say 1 times 2, or I could say negative 1 times negative 2, which means I would have plus or minus 1 and plus or minus 2. Now, the possible roots are going to be the ratio of the two of those. So I'm going to take all of my p-values and put it over the first q-value, 1 over 1 and 3 over 1, which means I have plus or minus 1 and I have plus or minus 3. I'm going to do the same thing with the 2. I'm going to put the 1 over the 2 and the 3 over the 2. I have plus or minus 1/2, and I have plus or minus 3/2. So before we had no idea where to go ahead and where to start with synthetic division. Now we at least have some options for us to go ahead and for us to take a look at. But that's 8 options, and I don't want to just go ahead and choose one and hope for the best. So instead, we've got this handy dandy calculator. We're going to go ahead, we're going to take a peek at what this graph looks like. I'm going to plug this into our y1. I have 2x to the third minus x squared minus x minus 3. And I'm going to go ahead and I'm going to graph it. Now notice I see that it only intersects the x-axis one time. This is a degree of 3, which means I'm looking for 3 roots. Since it's only intersecting it one time, I only have one real root. The other 2 are going to be imaginary. Now, of my 8 possibilities, I can eliminate all the negative ones. I am going to see it's going to be one of the positive ones there. 1, 3, 1/2, or 3/2. Well, taking a look here, this looks like this could be the 3/2. So I'm going to check the value. I'm going to do second trace. Number 1 is my value, and I'm just going to type in 3 divided by 2. And I see that, yes, it does go ahead. It gives me a 0 there, which tells me that that 3/2 is going to be one of the roots that work. This is going to be where I start to depress my polynomial. So I'm going to put the 3/2 on the outside. I have 2, -1, -1, and -3. I will drop down the 2. 2 times 3/2 gives me 3. Add down. 2 times 3/2 gives me 3. Add down. 2 times 3/2 gives me 3. Add down, and I've got 0. That's my remainder there, which means that I have f of x is going to be equal to, well, that 3/2 came from an x minus 3/2. And then what's left over? Well, I have 2x squared plus 2x plus 2. Now, if I'm looking at this one here, this 2x squared plus 2x plus 2, I could pull out a 2 out of all 3 of those pieces there. So really what I have is I have x minus 3/2. If I pull out the 2, and then pen's doing something funky there. So I have the 2, and then I have x squared plus x plus 1. Now this still looks a little bit weird here, okay? This 2 I can go ahead and I can back distribute in. Because when I see a factor, I typically don't see fractions in it. Anytime you have a fraction as one of your roots, you're going to be able to pull out a greatest common multiple somewhere, and you're going to be able to go ahead and distribute it back in. Okay, or greatest common factor, that's the word I was looking for there. So when I factor that 2 in, I'm left with 2x minus 3. Notice it cleared the fraction. And then I have x squared plus x plus 1. So this is completely factored. I know that because if there was other factors, I would have been able to see them on my graph as well. Let's go ahead, let's talk about the zeros now. Well, one of the zeros I found was x to be equal to 3/2. These other 2, I know are going to end up being imaginary solutions. If they were real solutions, they would have gone ahead and crossed the x-axis. So to find those imaginary solutions, I'm going to use my quadratic formula. I have x is equal to 1 plus or minus the square root of 1 squared minus 4 times 1 times 1 all over 2 times 1, which will give me 1 plus or minus the square root of -3 divided by 2, which is going to give me 1 plus or minus I root 3 over 2. All right, so originally the degree was 3, and take a look, I found 1, 2, 3 solutions. All right, let's go ahead, let's flip it on over, and let's take a look at another one. I want to list my possible rational roots, I want to factor it, and I want to find the zeros. So let's start with the p-values. Those are the factors of the constant. I have plus or minus 1, 2, 4, and 8. And then let's take a look at my factors of the leading coefficients. That's plus or minus 1 and plus or minus 2, which means my possible roots, I'm going to take 1, 2, 4, and 8 and put it over 1. So I'm just relisting those there again. And then I have 1 over 2, that's plus or minus 1/2. Well, 2 over 2 is 1, and I already have that. 4 over 2 is 2, and 8 over 2 is 4. So these are just my possible roots here. All right, so I'm going to go ahead. I'm going to plug that into my calculator. I have that is 2x to the third minus 3x squared minus 18x minus 8. Notice that this is degree 3, so I'm looking for 3 solutions. And if I notice, I've got 1, 2, 3 solutions there. So they are all real solutions. Well, let's take a look at some of these. I'm going to look at this one on the left-hand side first. 1, 2, that looks like it could be a negative 2. Let's check that value. Ooh, and that one works. All right. So x equals negative 2, that was one of my options that worked there. Let's see what else I have. This one off to the side here, 1, 2, 3, 4, looks like 4 could go ahead and work. So checking my value, 4 worked as well, x equals 4. Now here's the thing. If I have 2 rational solutions, the third one also has to be rational. You can't have just one irrational or one imaginary solution. All right, reason for that, think about where it comes from. It comes from the quadratic formula, which has a plus or minus in it. Irrationals and imaginaries will always come in pairs, which means that this third one also has to be rational. Looks like it's in between 0 and negative 1. I'm going to check that negative 1/2. And I see that that works as well. So x equals negative 1/2. I've gone ahead. I have found everything just looking at that graph. Okay, and sometimes that's going to happen. We love it when that happens, because instead of having to go ahead and depress and factor the polynomial, the work that you show me is just a quick sketch of what that graph looks like. And then you'll go ahead, you'll put in your x-intercepts. We had negative 2, 0. We had negative 1/2, 0. And we had 4, 0. And let's go ahead, let's think about where this comes from now. The negative 2 comes from an x plus 2. The negative 1/2 comes from an x plus 1/2. And then the 4 comes from an x minus 4. Now the only thing we really don't like is that x plus 1/2, but we can go ahead, we can clear that by multiplying through just this part by 2. And I'm going to see that f of x is going to be equal to x plus 2 times 2x plus 1 times x minus 4. This is completely factored. And then the zeros that I originally found from my graph, I have negative 2, 4, and negative 1/2. And obviously the order of those do not make a difference. Okay, but again, notice degree 3, 3 solutions. All right, go ahead, pause this video, find me the second part, please.